Okay, let me start the chapter 6 on the matrix displacement method. The name of this method implies that you guys are supposed to go back and review the mathematics called matrix. Okay, I will not go through this, but it's going to be your duty to review it. And then we talking about the displacement method. That means in this analysis for the task, we will use the displacement v sub x and v sub y as the unknown. We will use the displacement as the unknown. And then what going to be what? You got to go back again to not only review the matrix. I like you to go back and review the task analysis. We study the task analysis since the engineering static. Okay, and then what you study the task at that time is the statically determinate task. But the matrix displacement method will cover both statically determinate and statically indeterminate. You study the statically indeterminate task in the theory of structure. That means you may use different kind of method to check the answer that you may get from the matrix displacement method. No matter you study in these courses, the concept of analysis of task is still be the same. If you consider the task will joined by a linear small pieces of members, and most of the tasks are connected by a pin. So the joint of the task is pin, and I should say it's going to be the frictionless pin, theoretically pin. And then the task is subjected to the forces at the joint. That is going to be the second forces applied to the joint, So under this assumption, in the engineering static, we have the member of the task to be the two forces member is maybe subjected to tension, or is maybe subjected to the compression. When we said it's tension, usually we said it's going to be positive force, and the compression we said is going to be in the negative force. When you study the mechanics of material, when you study the design of the tension member in the chapter 1. However, for the compression member, you also study it not only in chapter 1, actually it's chapter 3 and chapter 4. It's also studied in the chapter 13, because the tension member is different from the compression. The tension member, the member will be in tension. However, in compression, the member can be buckling. Okay, so the design of the member are different. So when you analyze this, you got to tell me or tell the engineer that the force in tension or in compression. And then during the study of the engineering static or theory of structure, you use what's so-called the method of joints and also method of section to analyze the task. These two methods are different. The method of section is good when you analyze the task for the internal force in the interior of the task. But the method of joints is better for the member that's close to the support or only has two unknown forces. Okay, and I let you guys first joint, J-U-I-N-T. Joint is pin, frictionless pin. And second, the external force applied to the joints. And the member is going to be what's so-called the two force member, which is going to be in tension and in compression. And then during the theory of structure, you assume the third one. You assume what? Under the force, under the forces, the behavior of the material is what? Of the material is of the specificity, the steel or the aluminum is in linear elastic. What so-called is the behavior of this steel or the aluminum is going to be only in this yellow region. And then what else? The other part is just for the safety factor. And the fourth that we have under the forces, the truss has small deformation. Okay, so when you calculate for the unknown displacement, your deflection supposed to be very small, such as 5 millimeter. Okay, it won't be kind of 5 meter. That is wrong. Or it's maybe just 1 millimeter if the span is short. So that is for yourself. And the limitation of this method is included in the concept and the assumption already. Next, after you understand what I said in the learning objective 1, for the learning objective 2, I will use the concept, assumption, and the limitation to develop the matrix displacement method. Okay, and again, when talking about the matrix, that means you guys need to go back and review the matrix and practice to use your calculator to do what? To do the multiplication, to do the inversion of the matrix, and we do the plus the matrix, such as how the matrix A plus the matrix B, how the matrix A times the matrix B, how the matrix A get the inversion. So the calculator will be very important. I will grade your work based on the manual calculation, okay, by using the calculator. You may use the calculator such as the 9000 FX, 9000 series, or the algebra, the Casio, the algebra. Or if you prefer to use the Texas Instrument, it's okay. Any calculator that can do the matrix operation is all good enough. Okay, and then when we talking about the matrix structural analysis, you will write the matrix in the form of force equal to stiffness times the displacement. This is going to be the force metric. This is going to be the displacement metric. And then at the interval, this will call the stiffness matrix. And to be in full, it's going to be the truss and then global stiffness matrix. This is the stiffness matrix for the truss with the global coordinate. And then based on this, you're going to find the displacement. That means you start by determining this matrix, okay? And later you use this to determine the reaction, the member forces. This is going to be different from what you study in engineering static, right? Yes, in the engineering static, you start by compute for the reaction, and then you cut the section to determine the member force. And later in the theory of structure, you use this knowledge to determine the displacement of the truss. So this method is in the opposite. You start by compute the displacement and then the reaction and then the member forces. And you should be able to draw the elastic curve of the truss. Under the application of this, the truss will deform to a given shape, and the displacement that you determine will be used to draw the elastic curve of the truss. And the last one, I would like you guys to be able to use the structural analysis software in our university. We use the Substructure. Okay, you can download this program for our website, and then you should interpret the analysis result correctly, and you should compare the analytic result with the manual calculation. Okay, now let's come back and visit the task in our university. Most of the task is in the form of 3-dimension task. Okay, even though this task you can see is combined with 2 tasks on the left and on the right when you walk through it. Okay, one on the left and another one on the right. But since this task is the planar task, you can reduce the 2D, 3D task to the 2D task, and we call it the planar task. Okay, in the standard theory of structure, you must determine the load that's applied to this task based on the building code, based on the design code related design code. Okay, and from the load, you must do what's so-called the load distribution. That means you got to distribute the load from the from the floor to the beam. This one, for example, there is the weight that's on the floor, such as the dead load of the floor. This load will transfer to what? Will transfer to the beam. That's link between the task. Okay, and then this load will transfer from the beam into the joint of the task. That is the joint of the task. We just put it by a circle. Okay, and then the load for the task will be applied to the bottom joints, and you may assume or compute it, for example, to be 10 kilonewton, 10 kilonewton, 10 kilonewton, 10 kilonewton, and then this one 10 kilonewton, and then some of the load may apply here should be just only the half of that. So the load applied at the joints, and the joints as a frictionless pin. Ajahn, the construction of the joint is not the pin, it's from the welding. But don't worry, I have proved in the theory of structure by analysis, by using the computer program. No matter you assume this one to be fixed, or you may assume the joint to be pin. When the force applied only at the joints, okay, the member of the task will be the 2 force member. Mainly, it will taking care of the axial force. Okay, the shear force approximately 0. The bending moment that occur in the fixed joint approximately 0, or is negligible, very small compared to the axial forces. Okay, that is for our understanding. And then what you do next? When you do it, this task is statically determined. So based on the engineering static, you can analyze this task. You can design this task by using the mechanics of material. In this kind of matrix displacement method, you also need to input all the required things into the problem. First, in the matrix displacement method, you got to know about the global coordinate system, in which we already know it's going to be the typical X and Y system. Okay, it will follow the right hand rule. And most of the time when you put this one into the analysis, you may set this one as the X, okay, and this one to be the Y. And when you put it into the computer, you mark it. Let's say you mark it and then you drag the line in the substructure to this point. When you do it, the computer will say this is going to be the node number 1. This is going to be the node number 2. They will put the number and put the circle into it. And it will say this is going to be the member number 1. And next, if you put the mark into this and you draw the line here, again, this is going to be the node number 3. And the computer going to say this is going to be the member number 2. So what I'm saying here, under this, the second, you got to know about the node. The node typically to be the support or to be the joint. Okay, it can be joint, it can be support of the task. Okay, and then you got to know about the number, the member number, and I should say third is going to be the member number, or it's going to be the number of the member whatsoever you said. Number of member is going to be the number with the square, but the node is going to be the number with the circle. And then not only that, you also provide the local coordinate to the member. For example, if you put the member in this direction, you're going to set the local coordinate, the number 4 is going to be the local coordinate system. Okay, that's going to be in the direction when you mark this point, you drag the line to this point. Okay, this is going to be number 3, and it's going to be number 4, it's going to be number 5, and it's going to be number 6. Okay, and it's going to be number 3, number 4, number 5, and number 6, something like this. Okay, this is the important thing. The global coordinate is going to be the coordinate for the whole task. The local coordinate is going to be the coordinate for the member. Okay, and the last one you're going to put is going to be number 5. Okay, for the number 5, we are going to talking about the degree of freedom. Usually, every member has 2 degrees of freedom per choice. It's going to be the horizontal displacement and the vertical displacement. However, if you check over here, it's going to be the unconstrained degree of freedom, which is going to be different from what's so-called the constrained degree of freedom. The green, the pin, has the constrained degree of freedom. Okay, what I'm saying is going to be the constrained degree of freedom. It's going to be the degree of freedom that you know at the support. Okay, is occur at the support. For the pin, there is 2 of them. For the roller, there is only 1 constant degree of freedom, and another one is going to be the unconstrained or free, unconstrained degree of freedom. The unconstrained degree of freedom will change with what? Change with the load. Okay, when the load is large, this kind of yellow degree of freedom will change with the large load, such as changing from the 10 kilonewton to 20 kilonewton. The deflection here, the vertical deflection will be changed, but the degree of freedom over here will be zero, never change. Okay, so we separate the degree of freedom into two important ones. 5.1 is constrained degree of freedom and 5.2 is unconstrained degree of freedom. I will talk about this notation, these definitions later in detail for the following PowerPoint. There is the loop task. Okay, this is the loop task in our university, if you can see, and you can see by this, by following what? By following the theory of structure, you may assume the one-way load transfer from the metal sheet into the purlin. This is going to be the purlin. Sorry, it's supposed to be the like one. This is going to be the purlin, and then the weight that's applied into the purlin going to be the uniformly distributed load, and then the reaction of the purlin will apply to the truss. Okay, let us consider only the vertical load. This is going to be the model of the truss. Again, in the analysis of this truss is going to be the statically determinate truss. Just follow the ending static. You can analyze this truss. Okay, and then if you go a little bit further to this truss is not statically determinate. It's going to be statically indeterminate. It has 4 pins. Okay, at the support, you can reduce this truss from the 3-dimensional truss to the 2-dimensional truss, and it's going to be the arch truss. And you can check the degree of indeterminacy of this truss by checking of what? Of the known. This is going to be the unknown forces with the number of equations, and you can see this truss will have B plus R larger than 2J, and the degree of indeterminacy gonna be 5. I'm going to get you guys time to work on this. Okay, and actually for the real world, the task mostly for especially the big tasks used to support large forces, they are going to be the statically indeterminate task. So in the past, when you analyze this kind of task, it's going to be very tedious job. Okay, there is no computer. So you got to use your knowledge from the theory of structure, such as the method of consistent deformation or the Castiglione theorem, to analyze this kind of task. This kind of task very beautiful in my opinion, especially this one. And the senior engineer that's work on this task, they are very excellent. This kind of task lasts for many years before it's going to need the maintenance and it's going to need the replacement. Okay, so I arrived at the statically indeterminate task and the big tasks that require the computer to help or assist you guys to analyze it. Okay, this chapter has 2 problems. Let's you guys work on the problem 6.1 and 6.2 in my book. When you do the manual calculation, Okay, you must compare your manual calculation with the result from the substructure program. I would like to confirm your knowledge between hand calculation or manual calculation with the computer program. Now, let us come to discussion about the fundamental of the structural analysis. Let's you consider the first task. Okay, let's put the task in this manner. This task is a kind of simple task. Okay, it may be, for example, subjected to the force of 10 kilonewton here. So this is going to be the simple task that can be analyzed by using the engineering static. And later, after you use this task for a while, the requirement of the task may be changed. Okay, you may put the support such as the column to support this task to make it stronger, to make it stiffer. Okay, stiffer or more stiff, or to make it stronger to resist a larger forces by putting more support. This one you check the statically determinate task into the statically indeterminate task with 1 degree of indeterminacy. Okay, you may check the determinacy by B plus R and compare with the 2J. By doing this, how many B? Bar 1, 2, 3, 4, 5, and then you have 6. Now the reaction that you have is 1, 2, 3, 4, and 5. That's going to be 11. How many joints do you have? 1, 2, 3, 4, 5. So you have to have 2 equations per joint. It's going to be summation of x sub x equal to 0, summation of y equal to 0 for one joint. So you have the total of 10. So B plus R is larger than 2J by 1. This is going to be the task with degree of indeterminacy equal to 1. When you analyze this, for sure you're going to use the free body diagram and use the equation of equilibrium to solve it, right? But that means you won't have enough equation to use to solve for 11 unknown. That means you're going to use the method of consistent deformation. You separate this task into 2 tasks. One is going to be the statically determinate, as you have the knowledge from the engineering static. That task will subjected to the given load, and then you plus this task by another task that's subjected to the redundant force. Okay, by setting the force that occur here as the redundant force. You're going to put the B sub y. For example, let's say this point is the B. The reaction due to this roller to be the redundant. And now what we have is under application of the force, the task must deform in a new shape. And that's why we require you to draw the elastic curve. Let's say this is going to be the delta sub B. And this task also must be deformed to a new shape due to the unknown force B sub y. Since this is B sub y is the unknown, usually when you analyze this task, you set B sub y equal to 1. And then you determine the deflection at point B in the direction of B sub y. Since this force comes to only 1 unit load, so the total deflection is going to have B sub y. Now, you may have set up the compatibility condition in which the deflection at this point is 0 equal to the deflection of delta sub b, and then this is going to be plus minus of f sub bb b sub y since it's in the upward direction. So you get the equation b sub y equal to delta sub b divided by f sub bb. That is going to be the compatibility condition. To determine this, you must use your knowledge to determine the delta sub b, to determine the f sub bb. You have the knowledge from what's so-called the unit load method, for example, to analyze for the deflection of the truss. So you will get delta sub b, you will get f sub bb. We call this the force displacement relationship of the structure. That is from the theory of structure. Okay, that's why we study all of the subject step by step, and then based on the assumption that we use to analyze this one, which is going to be based on the principle of superposition. That means what? That means the behavior of the material under the application of the force going to be in the linear elastic range, and then also the deformation of the structure going to be small. By doing this, we say the material response under the applied forces going to be linear elastic. What I'm working on the task with the unknown forces, which call the redundant forces, and then we use the compatibility equation. We use the force displacement relationship to solve the problem. After we get the b sub y. Now, if you know the force of b sub y here, we can use the free body diagram and then the equation of equilibrium to solve for the internal forces of this truss. So for the reaction for this truss, and then you use the knowledge of mechanics of material to design this truss easily. Now we come to the next step. We're going to use the displacement as the unknown. By using the displacement as the unknown, we call the method is the displacement method, and then we use the mathematics of matrix to solve this. So by doing this, you're going to use the equation of equilibrium. I will tell you later the force relationship to set up for the force, and the force will separate into the no force and the unknown force. This is going to be unknown force, going to be the reaction, okay, and the no force, this one going to be the given load. I will give you the given loads that's tied to the structure, and this will be related to like a spring. For the spring force equal to stiffness times displacement, you will have this stiffness, and then this one will come with the displacement matrix. One is going to be the unknown displacement, and another one is going to be the known displacement. Okay, why you know the displacement? We know the displacement due to what? Due to the support. This is going to be the displacement at support of the truss. This is the reaction. The reaction is the force at the support of the truss. See? And then what we have inside this need some kind of derivation. We will go to this derivation later. But this matrix is called the stiffness matrix. Okay, it's called the stiffness matrix. and it's going to be called the truss, okay, stiffness, and then matrix. We're going to form this one. However, before you can find the truss stiffness matrix, you got to determine what's so-called the member stiffness matrix. Okay, that is going to be the first thing we determine. After we determine the member stiffness matrix, we put them together. We get this is going to be K11 is going to be K12 is going to be K21 is going to be K22. Okay, and then you will use the mathematics, follow the matrix to solve it. And since the computer can do the matrix manipulation easily, that's why we can programming this method into the computer and develop it as the computer program. Now, we come to the structural analysis software. You may download this one, the structure, or in the full name is going to be the Suryanuri University of Technology Structural Mentor Program. Okay, and this is going to be version 3.51 or something. This is free and it's very useful one, and it's used to be the top hit download software in the top civil for many years. And then there are a lot of composition software that you may use, such as the Revit by Autodesk. You may apply for the state license and then download this program to practice. And in the industry, you're going to use a lot of this thing. But anyway, the industry advisory board said it's better to teach the student to excellent in the manual computation first, because the manual computation will enhance the engine sense. And then when they use the computer, that engine sense will use to recheck the response of the structure that's computer generate. They are worried about this because if you put junk or misinformation into the computer, it will generate junk, not G, junk out of the computer program. Only the engine sense can be used to detect it. It's supposed to be in that kind of response or not. It must follow sense first before you accept the result of calculation. The matrix displacement method uses in many computer programs, or is more popular in the coding of such a software than the matrix force method, because it's what is can be easily, or it can be used directly to analyze statically determinate and statically indeterminate. Okay, and another thing is this method will give you analytical result directly. It can be used less computer resources in the computation. Okay, it's used smaller or less calculation step. And the last one is easier to coding the software. So most of the software that we are talking about is going to be that. Now, I did mention when we talking about the matrix displacement method, we will have the no forces. The no forces is going to be the Q sub K, and you will get the unknown forces. The unknown forces is going to be the reaction. So the first step, you got to find the known applied load from the problem. Okay, and then I will tell you later how can you find it. And you also be able to determine the known displacement that occur at the support, and then on the right hand side of the equation you will have d sub u, which is the unknown, and d sub k. You got to determine d sub k from the problem. You got to determine the applied forces, okay, and the known displacement from the problem. And then you will use the equation to determine the unknown the unknown displacement, okay, that is going to change with the magnitude, the change of the magnitude of the applied loading. When the applied forces and loading is large, the deformation, the displacement is going to be large. When the applied force small, the displacement and the reaction going to be small. How they are related between the forces and the displacement, like the spring, it related by the stiffness. And like I told you again, you got to do the partition. We separate partition the matrix into 4 of them, basis upon the partition of the force, basis on the partition of the displacement. And by using this kind of partition, you will calculate or you will do the matrix structural analysis easier. Now, I must put this one into the position. How do we use the mathematics to solve this? Okay, you may write the first one. This Q sub K is going to be equal to K sub 1, 1. Let me put it in back, K sub 1, 1. And this K sub 1, 1 will times D sub U, the unknown displacement. And then it's going to plus K sub 1, 2. This K sub 1, 2 must multiply by the D sub K. That means after do the multiplication, the matrix multiplication, you will determine this is in the form of the value. And then you may deduct it from the Q sub K. Now, by doing that, you will determine the equation of this to be the Q sub K minus K sub, what's so called K sub 1, 2, okay, times D sub K. That is going to be the matrix on the left. And this one will equal to K sub 1, 1 and times D sub U. By doing this, you can determine D sub U equal to the inverse of K sub 1, 1. I suppose to put it into this basket, inverse, okay? And then it's going to times the term over here. After you do this, you go back to use your calculator to do the matrix multiplication, to do the matrix subtraction or deduction, and do the matrix inversion. Go back, practice, and practice, okay? A lot of students have the problem with using the calculator in this one. Sometimes to use the computer in the analysis of this, but due to the requirement of the subject to use the computer is illegal. You must use the calculator to do the manual computation, follow the course learning outcome. And the computer will be used to check the result later. Okay, now you know. Now you can compute, and then this D sub U is known. You can then later to determine the reaction Q sub U. That is going to be very easy. It's going to be equal to K sub 2, 1. Okay, you may put the basket here, and then it's going to have the known D sub U, and then it's going to be what? Plus. Okay, previous one you have this one times this, plus this one K sub 2 times what? Times the D sub K. Now you just put everything into your calculator, compute this portion, combine them together, get this reaction. That is the process you got to do during the calculation. Okay, it's required very prudent action. You're supposed to be very cautious when you do the matrix structural analysis. Now, after you determine the reaction that occur on this structure, okay, and you also know the deformation of the structure, you can draw the elastic curve of this truss. Okay, you got to put it into the ruler. Okay, don't do it like me. You got to draw sorry, I draw the wrong one. This one, you got to draw it carefully, and then you may put this in. So after you compute the structure, you get the D sub U. This is going to be the unknown displacement. You get the Q sub U, which is the reaction. Now, the next step, you got to determine the internal forces. Okay, this one going to be require you to consider the member. For example, let us consider this member. Just take this member, and if you remember, this is going to have the node over here. The node over here. Let's call this one near N. This one, let's call the N. And let's call this one is far in, based on the local coordinate that's putting in this direction. And if you recall from the second slide, you will know the coordinate of this with respect to the global coordinate. For example, if this one is 0, 0, this is going to be 2, 0, this is going to be 4, 0, and this is going to be 6, 0 if the interval to be 2 meters each. So you get the near end to be 4, 0. Okay, and the far end also, this is 2 meters. So this is going to be 6, 2. So this is going to have the coordinate of 6, 2. And we call it to be x sub far end. It's the head of the arrow. It's called far end. And this is going to be y sub f far end. And this is going to be x sub n. And this is going to be x sub f. It's going to be in the number, okay? And if you may recall, you may put the number of this member, okay? It may be member number 10. This is going to be the near end of node 1. This is node 1, node 2, node 3. It may be node number 3. And this is 3, 4, 5, 6, 7, 8, 9, and then this is maybe node number 10. Member number 10 has the coordinate 4, 0 over here, have the coordinate of 6, 2 over here. Okay, if you want to follow me, stop the video clip and go to check it again. I'm going to talking about this because the alignment of the member of the task, some can be in the horizontal. Okay, some may be in the vertical, some may be in the incline. Okay, when the member has many directions, we got to specify the direction of the member. We specify the direction of the member by using the coordinate direction cosine. You will go back to the engineering static, okay, of this one to be cos theta sub x if this one is theta sub x. And the other way, we specify the angle here to be theta sub y, and we said this is lambda sub y equal to cosine theta sub y. And now you can compute to determine the direction of the member based on this. Okay, the definition of the coordinate direction cosine from the engineering static. Okay, you can determine the coordinate direction cosine theta x by using this one, the length here, and divided by the length of the member L. Now, if you calculate this is 4, this is 6, this is 4, this is going to be 6 minus 4, this is going to be 2 meters. Okay, this is going to be x sub f minus x sub n. And also, when you go to this one, the length over here will be what? Will be 2 minus 0. Okay, it's going to be 2 minus 0, and it's going to be 2 meters. And this is going to be y sub f minus y sub n. And then you determine the length of this member by what? By 2 square. The L is going to be square root the vertical 2 square minus the horizontal 2 square. This is going to be 2 square to meter. So the L can be determined from square root of this green one, x sub f minus x sub n square, y sub f minus y sub n square. Okay, you just put this thing into the computer. When the computer know the coordinate of your node, it's going to compute the length for you. Now, you come over here. The cosine of this is going to be x sub f minus n x sub n divided by L. It's going to be this one, or it's going to be this one for 2, and then divided by 2 square root 2. So this one is going to be 1 square root 2 as the coordinate direction angle lambda sub x. For the lambda sub y, this is going to be y sub f minus y sub n divided by L. Or following this is going to be 2 divided 2 by 2 square root 2. So this is going to be 1 square root 2 for lambda sub y. I let you guys to follow what I going to be. If you cannot understand, remember it. How to determine the length. How to determine x sub f minus f sub n. How to determine y sub f minus y sub m. How to determine the coordinate of the node. How to specify the node. How to specify the member. Those kind of things are defined in the computer program. When you put kit into this and that the line here, the computer know the node, the computer know the member, the computer know the coordinate, the computer can compute the coordinate direction cosine of each member. Okay, now why I talking about this? I'm talking about this because the member that we are talking about is going to have the forces inside it. It's going to have the internal force. Since this is the near end, this is the far end, the force occur over here. We call it Q sub F, the force at the far end, and the forces that occur here, okay, we call it Q sub N. Let me illustrate this one a little bit. The forces, this is the force at the near end, okay, and then due to the forces, the member must be deformed, okay. This member may be deformed like this, and then the deformation that occur here is the deformation at the near end, and the deformation that occur here is going to call the deformation at the far end, okay. And basis upon this, when you do the computation, you will have the force Q sub N, Q sub F is going to be the force, and then it's going to be equal to the stiffness of the member, and then it's going to time the displacement that occur here. That is going to be the Q sub N and Q sub F. Now, the force related to the displacement, and in this time, the matrix here will be called the member stiffness matrix. But this member stiffness matrix is based on the direction here. The direction here is going to be based on the axis X palm here, Y palm here. We call this as the local member stiffness matrix based on the X palm, Y palm. There are a lot of definitions Ajahn has explained for 60 minutes already. You guys must be understand this, okay? And the knowledge of this come from the mechanics of material, basis on what? If you go back and you recall the sigma equal to E epsilon, this is what? This is Hooke's law. And then for the sigma is going to be Q divided by A. And this is going to be equal to E times the strain, which is going to be small d divided by the length L. So in short, basis on the previous knowledge, you will have Q equal to something that's talking about the D going to be here, and the internal force from this causes will be related to the displacement. And then you can see inside here going to be E times A divided by L. E is what? Is the modulus of elasticity. L is the length. And then the A is going to be the cross-sectional area. Okay, and this called the member Truss stiffness, or just the member stiffness, because Truss is the axial load, axial to force member, or the axial load member. Okay, so just I like you to recall about this for the chapter 4 of the mechanics of material. So what the whole thing is, we are going to review what I have lectured to you for the previous 60 minutes. We come to a simple task. Okay, why I call this simple task? Because this task has the pin support here, has the roller support here. And then when you're going to analyze the task following the matrix displacement method, you're going to follow some specific procedure. First, we talking about the global coordinate system X, Y. Okay, let me put it like this. It's going to be the global coordinate X, Y. And then we talking about we putting this structure into a computer program. We mark it. When you mark it, this one will be node number 1. And then you drag the line across this one. And then end over here. The computer will know this is going to be node number 2. Okay, the number with the circle. And then the computer will know this is going to be member number 1. And then the computer will know the local coordinate going to be in this direction. So the global coordinates x palm, v palm specified by putting this point that hit along the line, and over here put the mouse off. And then you also know about the node number, okay, with the number. And you also know about the member number. Now, you do again, you put the point over here, okay, number 2, and then you drag the line across this one. So example, you drag this one and end over here. Okay, sorry, number 3 first. This is the wrong one. We'll drag the line across this one to be number 3 here. And then you drag this, you drop the mouse off. And then they said this is going to be the node number 3. Okay, this is going to be the node number 3. And then it's going to, that's not correct here. Because follow the node number 2 first. This is not correct. Okay, anyway, do that over here. Okay, it said this is going to be the node number 2. The member number 2. Actually, this is supposed to be node number 3. This is going to be the node number 3, member number 2, and in the local coordinate in this direction. Okay, and then they said this is going to mark for the node number 3. You may mark this one for the node number 3, and then you drag the line across this. This is going to be this one, take off. That's going to be the member number 3 with the local coordinate in this direction. The computer will generate everything. And then you come to this point, you mark this, and then you drag the line across this. This is going to be the member number 4 with the direction in the local coordinate direction. Okay, and then you mark for the member number 5, you drag it, and then you drop it out. This is going to be member number 5 with the local coordinate in this direction. So the first one already know the global coordinate, the local coordinate, the node number, the displacement number, all of that are specified by you and given the number by the computer. And then you also know the coordinate of this. This is going to be 0, 0. Okay, since this is 0, 0, after you put the point here, it's going to say this is going to be 0 and then minus, for example, minus 2. Okay, and then when you mark it to this point, you move it in this point, the computer also knows it to be, for example, 4. And then in the x direction, sorry, it's going to be 4. In the y direction, it's going to be minus 2. And then when you drag it to this point, it's going to say it's going to be 4. And this measure upward 1 meter from the left front. And also this one may be in the x of 2 and in the vertical of 1. You also know the coordinate, okay, coordinate of node. When you know the coordinates of node, later the computer will use the algorithm to determine the lambda sub x, determine the lambda sub y for each member. Okay, the member 1 will have their own lambda sub x, lambda sub y1. Member 2 also will have. And then there is one very important thing. You got to determine the degree of freedom. And I said the degree of freedom separate into 2 types of kit. One is going to be the constraint. Okay, the constrained degree of freedom. And another one is going to be the unconstrained degree of freedom. Unconstrained degree of freedom. You got to go to the textbook of Hibbeler and go to all of this. And then what? The constant degree of freedom will occur at what? Will occur at the support of the task. Okay, that means this is the pin. Okay, this one going to be the constraint degree of freedom, and this one also the constraint degree of freedom. For the unconstrained degree of freedom is going to be this one, 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 is going to be this one. This is going to provide you the unknown degree of freedoms. Okay, this is going to provide you the known degree of freedom. Okay, and then based upon this, not only the known or unknown degree of freedom, you supposed to find another thing. This degree of freedom will provide you with the forces matrix. Okay, it's going to produce the displacement matrix. This one has been discussed, and you can see the known degree of freedom at this one will provide you with the reactions, which is going to be Q sub U. And this unknown degree of freedom will be the node for the applied forces. This is going to be Q sub K. Okay. Oh, Ajahn, there's a lot of things. Stop video and try to think, follow what I'm saying. The degree of freedom separate into 2 of them. One, the light blue. Okay. And this light blue also related to the reaction. Okay. It's at the support. And another one, the unconstrained degree of freedom, the green one. Okay. That's related to the applied forces. Applied forces may be applied to this one 10 kilonewton, and this one for 10 kilonewton, and this one for 5 kilonewton, and this one for 5 kilonewton, and this one again for 10 kilonewton. All of the whole forces is going to be the Q sub U. That will generate the reaction here. And then how do we number them? Okay, and we're talking about to be number them later. So global coordinate, local coordinate, number of node, number of member, and the degree of freedom. Now This is the no apply load. How do we separate it? In this matrix, okay, in this computation again, we said it's going to be Q sub K. Follow the Q sub U. In order you guys can use the mathematics, or we'll use the matrix to solve it. This is going to be D sub U, and this is going to be D sub K, and this separate into 4 partitions. Go back to what we have it before in the previous slide. Do I show you over here? See, this is Q sub U. Sorry, this is Q sub K. This is no force. This is Q sub U, reaction. And this is D sub U, unknown displacement. This is the no displacement. And for K inside it, we come to this point again. Okay, and then what do we have is the known force. Follow this 5 degrees of freedom. Q, capital Q1, 2, 3, 4, and 5. Okay, and then you also have D sub U, D, capital D, 1, 2, 3, 4, and 5. And later you have the reaction Q7, sorry, Q6, capital Q6, capital Q7, capital Q8. And then you have the known displacement at the support. That's going to be the constraint degree of freedom at the degree of freedom 6, 7, 8, and the unconstrained degree of freedom over here. Let me erase it, and that is going to be at the what? At the green degree of freedom. And this is going to be the known applied loading. This is going to be the known displacement. This is going to be known, okay? And this is going to be known. We're going to use the mathematics, the matrix manipulation to determine the unknown displacement and unknown reaction. Now, the degree of freedom can be separated to the constant degree of freedom and separate into the unconstrained degree of freedom. The unconstrained degree of freedom come before the constant degree of freedom, and then it's come from X and then Y. 1, 2, 3, 4, and then we have one more is 5. You can see the unconstrained before the constant won't follow this XY. Okay, it's covered, and then it's come to the constant degree of freedom. That's 6, 7, 6, and then 7 in X and 8 in Y. You must follow this step. You must follow this order. The order we want, the order will come from the unconstant degree of freedom, okay, with the X and then Y, X, Y, X, Y. However, for some special case like this, it's going to go 1, 5, and then later come to the unconstant degree of freedom, 6, 7, 8. Go back and try to rebuild it. The conclusion is going to be the 1, 2, 3, 4, 5, and then 6, 7, 8, following the note that I provide you over here. Okay, and then you can see following the result of this. This one of what? This one follow the degree of freedom number 2. This one will follow the degree of freedom number 1. So D1 is going to be positive, and then the D2 is going to be negative. Okay, now you come and check over here. D3 has 0 value. D3 for now is 0. And then down here, D4 is going to be negative. And also D5 is going to be here. This is D5. This is D4. This is going to be D1. This is D2. D3 equal to 0. Okay, you must follow this sign convention also. Positive or negative is going to reference to the global coordinate system. Okay, and then we go a little further after this. After we know the degree of freedom, we can determine the Q sub K, and we can determine the the D sub K. Okay, we will have the matrix in the form like this, and then by following this form, you going to use the stiffness matrix. This is going to be one important thing. Now, what stiffness matrix? The stiffness matrix will have the size. The Truss-Member matrix will have the size of degree of freedom by degree of freedom. But this is the Truss-Member matrix. The Truss-Member matrix must be determined from the member global stiffness matrix K. This is important one. Let's see. If you consider a member, this member number one, okay, will provide K1. This member number 2 will provide K2. This member number 3 will provide K3, and this is K4, and this is K5. Okay, each of them will, which member must be determined first, and then you may later combine them to be the Truss-Stiffness matrix, which is going to be the capital K matrix. So what is it? When you come to the small k, okay, there are the coordinate direction cosine lambda sub x and lambda sub y. This is going to be x sub f minus x sub n divided by L. This is going to be y sub f minus y sub m divided by L. So what is important? You got to go back and check out the coordinate that we has mentioned before, 0 to 4 minus 2, those kind of things. We come to this one, okay? This one going to be 0 minus 2, for example. This one going to be what? 4 minus 2. And this one going to be 4, 1. This is going to be 2, 1. We're going to use this one to do the computation for the coordinate direction cosine. Okay, for example, if you prefer to determine the member number 4, okay, you're going to have lambda sub x for number 4. That is going to be the x sub f is going to be 2 minus 4 divided by, this is 2 minus 4 divided by the length. The length is going to be what? This is going to be 2 meters. This is going to be 2 meters. So it's going to be divided by 2 square root 2. That is going to be minus of what? Minus of 1 square root 2. Okay, and if you like to determine lambda sub y, this is going to be 1 y sub f. Okay, y sub 1 minus of minus 2. Okay, this is going to be 1, and then minus of minus 2, and divided by 2 square root 2. This is going to be plus. This will be plus, right? 1 minus 2. That is correct, right? That is correct. Y or this plus 1, and this is 2. X sub f going to be 1. S y sub f, y sub n. Okay, and this is going to be the lambda sub y. Okay, and then what we have is we're going to put the lambda sub x and lambda sub y in this matrix. I will talking about this matrix, how this matrix come later. How this matrix come later. Oh, sorry. This is 1 minus. Oh, not quite correct. Anyway, let's check later. No, it's don't worry. Later, after you get this lambda sub x and this, you can see this one and this one will be square. And then they time it here. And you can see this block is the same as this block. You just copy it and put it into this. And also, you may notice this block is the negative of the first one, and this block is the negative of the first one. So the small k is very easy to determine after you can determine the correct coordinate direction angle. And then it's going to time by the member stiffness. Okay, the one that I has shown you before is come from where? It's come from somewhere over here. That's very far away. Okay, that's over here. No, not yet. The old knowledge that we discussed about the stiffness from the mechanics of material. I cannot find now. But anyway, not yet. Not this one. I forgot. The mechanics of material. Okay, don't worry, we get the stiffness before. S is going to be the same one. A is the area, E is the modulus of elasticity, L is the length. Okay, and this matrix is the square matrix. Okay, it's going to be 4 by 4 matrix, and it's symmetric matrix. What is mean if by following what I just lecture you, the matrix must be in symmetric matrix. What is mean is going to be this member is the same. This one and this one going to be the same. This one and this one going to be this one and this one, this one and this one and this one and this one. It's going to be symmetric across the diagonal member. And then we will combine small k1 to k5 to the capital K, and then you get this matrix as I explained to you guys before. And the no forces going to be here. This is going to be the no forces. Follow the unconstrained degree of freedom, and you're going to determine the unknown displacement. And then this is going to be the known displacement, and you're going to determine the reaction by following the matrix calculation. And then based upon this, you will have this one. You must use the matrix operation to determine this one. For this one, you can see this Q sub K, okay, will equal to K sub 1 times D sub U, and then plus K sub 1 times D sub K. This is going to be a number, okay, and then this one will interact with this one, okay, and then again later you can use the mathematics to determine the D sub U. When you know D sub U later, this is known, okay, by your computation. You then later to find Q sub U. Q sub U equal to, by this equation, Q sub U equal to K sub 21 times this one, and then plus K sub 22 times this one, and then you put everything into your calculator, you will get the result. Okay, now you get the reaction. This is the reaction. You got to determine the force inside the member. Okay, the force inside the member will determine by this matrix. Again, AE over L, you know it already. Okay, the member that we has discussed, we can determine the lambda sub x number 4, lambda sub y number 4. For the force in the number 4, you just put this one into this position, and then this one going to be the near end, this one going to be the far end. So the degree of freedom will be 3, 4, and then 1, and then 2. You have this one, you know this already from this one, and you know this everything from the calculation of the small k matrix. So you get the force inside each member, and when you can check the force inside the member must be in equilibrium. And if you get the positive, it's going to be in tension. If you get the negative, it's going to be in compression. Okay, that's a lot of lecture. Yes, that's a lot of lecture. So review it again. Global coordinate system. This is for the coordinate system for the capital Q and capital D. Okay, the final product from this calculation will be assessed on this. And then during the calculation, you got to determine the K matrix. Okay, before you can get the K matrix, you got to know the lambda sub x, you got to know the lambda sub y. Before you determine this, you got to know the coordinate, okay, at near end and far end. Okay, before you know the coordinate, you got to set up the local coordinate x, y. Follow when you deck this one, you deck this in this position, so you got this direction. Okay, and that's based on the x palm y palm direction. Its origin is at the near end, and then the x palm will go along it, and then it will follow the right hand rule. Just follow the right hand rule. You know y palm here, then you know the x palm here, then you know the y palm. The member, just the number with the circle. That's the note. The member is just the number with the small enclosed square. Okay, small enclosed square. The member is going to be enclosed by the circle, and then you can see by checking the arrow here, and then this is going to be near end, and this is going to be the far end, and the specification of this member will be like this. Okay, will be like this, and then the degree of freedom separate into unconstant degree of freedom, in which is going to be this one, is going to be this one, this one, this one, and this one, and then followed by the constant degree of freedom, follow the support roller, and follow the support here for the pin, and number rearrange for the unconstant degree of freedom, the green 1, 2, 3, 4, 5, and then the constant degree of freedom 6, 7, 8. Now we require to determine the K matrix. Before we can find the member global stiffness matrix, we will start by the local Truss-Member stiffness matrix K palm first. And like I tell you before, we have what? We have stress equal to modulus of elasticity, put the state, and then we have Q divided by A, which is the stress, is going to be E, and then small d divided by L. So Q equal to EA over L, E times A over L, and times D. That is going to be the stiffness, okay, of a member. But we consider not only in one direction, we consider in two directions, in the near end and is in the far end. So by doing this, our Q we separate into Q as the near end and Q as the far end. The displacement will be the displacement at the end and the displacement at the far end. So we got to separate, consider this by using the principle of superposition. Again, we'll separate this consideration into one with the near end, another one is the far end, and then this assumption apply. Okay, and at the near end we can use this equation to determine our relationship. Okay, and at the far end we also can use this one, and then we combine them by the principle of superposition. We will find the K palms matrix. Okay, the first one, the Q palm, follow that, and then the Q sub F palm. How is palm? Just summation of x sub x palm equal to 0. When you know this force, you will know this force in the opposite direction. The same also apply for the far end. Okay, and then you can combine them together by putting this one together. For the near end, you're going to determine Q sub F. Q sub N. The Q sub N is going to be this term, and then plus this term. You got this one for the negative. And on the top, you got Q sub F, and then you got Q sub F, two of them. Okay, one you put it over here for the positive, and this is negative, you put it over here. Now you like it Q sub N, Q sub F. This is the force, is going to times the stiffness, and this is going to be D sub N and D sub F. And following this, you have AE over L, AE over L, D sub N. You have minus AE over L, D sub F. And then for another one, this one, you have AE over L, D sub F. So you must put this one over here. You have the minus AE over L, D sub N. You have this one. So you got the K palm matrix in this form. And this one called small q, internal forces, equal to K palm matrix in the local coordinate times the local displacement. And then you come to another thing. You got to find the K palm. Okay, really, you got to find the K matrix. K matrix is based on the global coordinate. So it's based on how the member align itself on the truss. So based on that, we got to use the coordinate direction angle or direction cosine, coordinate direction cosine to determine it. We have the coordinate direction angle theta x here and coordinate direction angle theta sub y here. Based on this, we will find lambda sub y. We will find the lambda sub x, which is going to be cosine theta x by the definition of direction cosine. This is going to be cosine theta sub y. And then again, coming into this, since this one with respect to the global coordinate 0, 0. So you can use this reference to determine x sub n, y sub n. Okay, it's going to be the local coordinate. Oh, sorry, it's going to be the global coordinate here. This is going to be y sub x sub f and y sub f. For example, if this is going to be, let's call it x sub n. Okay, and y sub n. And this one is going to be x sub f and then y sub f. Okay, this one may be 2 for the x and 1. Okay, this one may be 4. Okay, and then it's maybe 3. Just read it. The computer program will generate this kind of coordinate when you put the point onto the screen, and that the line at the end, when you remove the mouse, it will be provide the coordinate. And then what is going to be lambda sub x? Lambda sub x is cosine theta x. How we determine the cosine theta x is going to be the rate divided by the length over here. Okay, and that is going to be what? The rate. This is going to be x sub f minus x sub n. Okay, and you may also know that this one will be y sub f minus y sub n. Okay, and then based on this, you will have x sub f minus x sub n divided by L. And this one also, you will have this one for y sub f, this one. And then minus y sub n divided by L. What is L? L is going to be this length square plus this length square root. So L is going to be x sub f minus s sub n square plus y sub f minus y sub n square and then square root. Okay, so the definition of this one will come from what I'm derived here to show you. It's come from our previous knowledge of the engineering statistics. You go to the textbook of Hibbler, chapter 2. Okay, you will see this coordinate. Actually, it said coordinate, direction, cosine. Okay, and that textbook is called alpha, beta, gamma. But this is only in 2 dimensions. So this is going to be cos alpha, and this is going to be cos beta. Following that's very easy. Now we're going to work on the relationship between the deformation of the member with the displacement of the truss in the global coordinate. This deformation of the member is in the local coordinate. Okay, so you have d sub nx. You like to determine this, you can cosine it. The angle here is going to be cosine theta x like this. So you can see you have this small arrow as the d sub nx cos theta x. Okay, and this one also you have this one, this d sub ny, you project it. You have this one for d sub ny. And the combination of these two is going to be the what? The d sub n. Okay, and the combination is d sub n. D sub n is going to be the portion of d sub nx cosine theta x bok this plus d sub ny cosine theta y. For this one also similar. You may project this one to be into this d sub fx cos theta x. Okay, and this one you may project this one for d sub fy cos theta y, and then you combine them together, you get d sub fy. Now you can write the equation for the d sub n, d sub n, d sub f in the relationship with the capital. They are capital. This one d sub nx, this one d sub ny this one d sub f x, this one d sub f y in this manner. And we call this one as the transformation metric. It's transform the displacement in the local coordinate into the displacement in the global coordinate. So this is called the displacement transformation matrix. So next one is force transformation matrix. This one uses the equation of equilibrium, okay, equilibrium to balance it. You can see you have Q sub Nx, you have Q sub Ny here, okay. You project this one. This is going to be theta sub x. You have this one Q sub Nx equal to Q sub N cos theta sub x. And for this one is theta sub y. You can have this one to be Q sub N cos theta sub y. The same thing occur here. This is Q sub x cos theta x, okay, and another one is Q sub f cos theta y, because this is going to be the theta y. Then you may see we have the rearrange it. Now we can find the relationship between the capital Q or the external force with the internal force small q, and you may have them in this direction and in this form. And since this metric is in this direction, is in the opposite to the matrix here, okay, this one is displacement transformation matrix. Another one that we get is called force transformation matrix. They are transport to each other. Since they are transport to each other, this is going to be transport. We call it transport. Okay, we just put the symbol into it. Oh, what is mean by transport? The row check into the column, and in the opposite, the column check into the row. They are transport to each other. Okay, and then you get this one, and then just put this one over here. You get this important equation, and if you may a little bit recall, this will use to determine the internal forces, okay, in the Truss-Member. And then from force transformation matrix, you put this Q into it, you rearrange it, and then you get the relationship between the external force or global force with the global displacement, and you arrive as this important matrix is called small k matrix or the member global stiffness matrix. You got to put these together, okay, and then you get the same form as before. And I should mention again, this form can be remembered easily. This one copy into this, and then later reverse the side in front of it, put into this form, okay? And then you can see this is square matrix and systematic. You put the small k together, you get the capital K matrix, and the capital K matrix can be separated like this. And again, you should note this is the no force and the no displacement. This the unknown force and the unknown displacement, and then the computation of what we like will perform like this based on the matrix computation. Now you got to follow this procedure again, okay? When you get this, you got to do everything we did mention about it. You separate this one. This is the unconstrained degree of freedom, okay? And this is going to be the applied forces. And then we have this one for the applied forces. Another one, you have the constant degree of freedom. That is going to be the known displacement. Okay, and then you can determine the small k. If you come to the member number 3, this is going to be the near end, and this is going to be the far end. When you rearrange it, it's going to be 1, 2, and then going to be 1, 2, 1, 2, and this is going to be 1, 2, and then the head is going to be 7, 8. That is going to be 7, 8, 7, 8 like this. So you just follow this computation procedure. It's not that hard. You know this, and then the author you will know it. You come to member number 4. Now for the member number 4, you have this one for the near end 3, 4, 3, 4, and then this one 1, 2, 1, 2, 3, 4, 1, 2 like this. You get this one in the form. This is the matrix, okay, that you got to determine. There is 2 things you determine for this. You got to determine the order of degree of freedom. You got to determine the members of this small k matrix, okay, and then you got to put them together. Since there are the total of 8 degrees of freedom, this is going to be 8 by 8, okay? And then come to the K1. K1 is over here. This is member number 1. Member number 1 has what? 7, 8, 3, 4. Okay, it's going to be 7, 8, 3, 4. And it's going to be 7, 8, 3, 4. The matrix will be something like this. This is going to be K1 matrix. When you put this thing in this form, just follow this. This is going to be 7, 7. Okay, and then 8, 3, 4. Go to the number 7. 7, 8, 3, 4. Okay, 7, 8, 3, 4. And then go to the row number 8. Repeat it. 7, 8, 3, 4. Follow it. 7, 8, 3, 4. And then go to number 3. Over here. 7, 8, 3, 4. You just do it very easy. And then go to number 4. Here. 7, 8, 3, 4. You get the first one. And then you come to the K2. Okay, we have K2. K2 is over here. You have the member number 2. That is going to be what? 3, 4, and then 6, 5. It's going to be 3, 4, 3, 4, and then you have it for 6, 5. You come to number 3. Number 3, you have what? 3, 4, 6, 5. You have 3, 4, 6, 5. Okay, 3, 4, 6, 5. And then you come to the 4. Come to the 4 here. Do it again. 3, 4, 6, 5. 3, 4, 6, 5. And then do it again for 6. You go to number 6. 3, 4, 6, 5. Just put the number into it. And then the last one is number 5. Okay, number 5 is here. 3, 4, 6, 5. You get this second K into the matrix. Now, the last one is K3. The K3 is here. We have the K3. K3 is going to be the 1, 2, 7, 8. 1, 2, 7, 8. 1, 2, 7, 8. You got to put it. And then you go to number 1. Number 1 is here. 1, 2, 7, 8. Okay, that is going to be 1, 2, 7, 8. And then go to number 2. 1, 2. And this one is 1. Sorry, 1, 2, 7, 8. just follow 1 to 7, 8, and then number 7, 1 to 7, 8, and then number 8, 1 to 7, 8. You can see some of them will be at the same slot. Okay, some of them going to be 0 value, and then you do this computation. You just do the partition, the matrix into something like this, and I like to spell it again. This is known. This portion is known. Okay, this portion is known. You find it in very first step of computation. This is going to be the unknown. You start by determine this one, and this is going to be the reaction. Okay, it's also be the unknown. Then you get this form, and then you do the computation as you supposed to be. Okay, and then you find the internal force. Okay, just put this one, put into this one, you get the equation in the form like this. And I should mention that only Q sub F is used in this computation because Q sub F equal to minus Q sub N. And since Q sub F follow the positive X prime value, so we use this one to represent Q sub M. And if it's positive, it's going to be in tension. Okay, and that's all for today.